We're about to hear the presentation from the University of Miami team, the Water Boys, on a non-point runoff analysis and potential remediation of the upper Almendares River using low-impact riparian buffers. That was a mouthful.
Right.
Good morning, everyone. Today we're going to present our project, Non-Point Runoff Analysis and Potential Remediation of the Upper Almendares River using Low-Impact Riparian Buffers. The team.
Good morning. My name is Eric Antman. I am working on my master's degree in civil engineering here at the University of Miami. I am also an intern with Hazen and Sawyer PC, which I will join full-time when I graduate this June. And I am a native of the beautiful city of Fort Lauderdale, Florida.
Good morning. My name is Miguel Mesquat. I'm currently majoring in civil and architectural engineering at the University of Miami. I am from Havana, Cuba, and I was raised in the Almendares watershed.
Good morning. My name is Sergio Claude. I'm a senior majoring in civil engineering. I'm from the valleys of Cochabamba, Bolivia, and I'm currently looking for a job.
And my name is Leonard Barrera Allen. I'm a senior at the University of Miami. I'm a civil engineering major. Currently, I'm interning at Cumming Cedarburg Coastal Marine Engineering, which I will be joining when I graduate. I'm from Panama, Republic of Panama. So let's get started with our agenda for today. I'm going to be giving you the introduction. Eric will be presenting the methodology. Miguel will be talking about the modeling. And finally, the conclusion and assessment of our remediation will be presented by Sergio. So let's establish the reason why we chose this project and take you through the pathway from field to tap that causes a public health issue. Here we have a map of the Almendares Vento watershed, which is delineated by two different locations. We have the upper Almendares, which is delineated in blue, and and the lower Almendares, which is delineated in red. The yellow line that runs from east to west is the Almendares River, which is about 50 kilometers long. And the mass in the middle of the map is the Ejército Rebelde Reservoir, which is an artificial reservoir. Below these hydrogeological features, we have a Vento aquifer, which we'll go into depth later. Here are some callouts from some point of references. We have the Havana Harbor, the downtown Havana, and the Jose Marti International Airport. Now, the problem is that the Ejército Rebelde Reservoir penetrates into the Vento aquifer, which provides water for about 47% of Havana's population, that is over 1 million people. This means that the Ejército Rebelde Reservoir serves as a conduit for contaminants to Havana's water supply. Last year, we evaluated point sources of pollution within the Upper Almendares River, and we identified 3 of them within the Upper Almendares. One, a steel mill, a brewery, and a sanitary outfall. This year, we're going to be looking at non-point sources of pollution, which arise from agricultural and urban runoff. During a presentation with the Cuban Heritage Collection, we were approached by a landscape architect, Dr. Juan Bueno, from the Florida International University, who suggested the use of riparian buffers, which are vegetated strips lined along the river in order to treat these non-point sources of pollution. So the objectives we want to go through today is to quantify the non-point loads. We want to determine the status of the reservoir. We want to design the riparian buffer. And finally, we want to assess the performance of our remediation. Now Eric will continue with the methodology.
Thank you very much, Leonard. So when we go about our methodology, the first thing we want to do is we want to quantify the non-point loads which are entering the Upper Almendares watershed. And I apologize in advance for my raspy voice today. So moving right along, there are 3 fundamental processes in non-point runoff which we need to capture within our model. The first is the hydrology. And this is very similar to the module that we developed last year for addressing point sources, because there are some topographical features of the area which we recorded using a satellite-based remote sensing technology. And this topography controls the way that water flows through the area, and therefore the way that water picks up non-point contamination and moves it through the area. Last year, when we were dealing with point sources, our life was very convenient, because we know where the point sources are, we know what sort of contamination they release. So with just this module, we were able to figure out what their impact was on the river. Unfortunately, non-point sources, life is not so simple, because the non-point sources, the generation of pollutants is inherently diffuse. It depends on land use data. Typically, to determine land use, we could use a census data, land surveys, other demographic information. Unfortunately, in Cuba, we're dealing with a data-poor situation. Therefore, we went ahead and developed a generation module. You see here we have a cow. The cow produces manure. The manure is high in nitrogen and phosphorus. When it's used as a fertilizer spread about the land, the nitrogen and phosphorus run off. You fertilize the land. Unfortunately, you also fertilize the lake and the river, which causes quite some trouble. So the way we carry this out is using a technique called multispectral imaging. And once we had the result from the generation module, we then also developed a new technique in the runoff module, in which we integrated the results from our land use analysis in the generation module into the existing hydrologic model to determine how the varying land uses would cause the distribution of non-point runoff through the area. So to start, within the generation module, we used a technique called multispectral imaging. And multispectral imaging is not a new technology. It's been used for several decades for agricultural, taxation, and other purposes. However, to our knowledge, we are the first group to develop a multispectral method for addressing surface water issues. And the way the technique works is we have here the electromagnetic spectrum, and we have here the very narrow visible range. And we see chlorophyll, which is green, is right in the visible range. So simply using an optical image, it would be very simple to identify chlorophyll. The trouble is that chlorophyll does not necessarily mean agriculture. There's plenty of natural vegetation that has plenty of chlorophyll in it. So we're also looking for irrigation. And the best signature of moving water from irrigation is in the near infrared range, which is not visible to humans. Fortunately, we used a satellite called the Landsat satellite, which is capable of viewing almost an order of magnitude more wavelengths than the human eye can, and it successfully captures this near infrared range. So the way this works is we have here a Landsat satellite, which is operated jointly by NASA and the United States Geological Survey. The satellite orbits the Earth. The program's been going on since 1972, and it has a camera-like apparatus that takes snapshots of the Earth, except that it does so in the 8 bands of its very wide spectrum, instead of simply the red, green, and blue that us humans can see. So to determine how well our model worked, we decided to do a historical analysis. Starting out in 1985, let's think of what's going on in the world in 1985. The Soviet Union is still very active. The Soviet Union is Cuba's greatest supplier of foodstuffs, agricultural products, and other things. So when we look at our agricultural utilization of the land, there's very little of it. This is consistent with the historical record because Cuba is importing a great deal of its foodstuffs. Moving right along to 1989. 1989 is a very significant year in world history because of the fall of the Berlin Wall, the collapse of the Soviet Union, and all of a sudden Cuba was in a very bad situation because Cuba just lost the trade partner that it was dependent on for decades and needed an alternative supply of food. As Dr. Belt mentioned earlier today, there was the special economic period during which there was far greater production of agricultural foodstuffs in the area. People were growing vegetables in their backyards and depending on these vegetables for subsistence. So as we can see here, our model correctly captured what was going on in the real world and is therefore consistent with the historical and historiographical record. Because as we could see, agriculture in the area simply explodes in 1989. Moving forward to 1999, this is the tail end of the special economic period. We could see our agriculture is still very active, but when we click one slide further to 2002, it drops precipitously. Once again, this is consistent with the historical record because we know around this time Cuba was ending the special period, was finding alternative sources for foodstuffs. So we are very happy how our new multispectral methodology is consistent with the historical record, and therefore we believe it's a very accurate base for drawing our water quality estimates. And now we're going to move into 2013. A lot of very interesting things are happening in Cuba, because we hear that there's some more support for starting small businesses and other very small, very limited private enterprise. And that also seems to be consistent with our model, because not only are we seeing greater agricultural land use, we're also seeing much smaller, more diffuse plots than we saw during the special economic period. You notice these black blotches, that's simply due to an electrical fault in NASA's system. And in our analysis in the paper, we use a correction factor provided by NASA, so you could disregard those. And the end result of this is we now know the area of the land within the watershed which is being used for agricultural purposes, which Miguel will use to help develop a remediation.
Thank you, Eric. Now that we have this information, our goal is to assess the current water quality of the Ejército Rebelde Reservoir. In order to do this, we're going to use nitrogen and phosphorus as measure. So we determined the annual nutrient loading of nitrogen and phosphorus from the city of Cotorro and the agricultural lands in the Upper Almendares watershed. To do this, we first determined the annual rainfall in the city of Havana. Then we determined the runoff coefficient, which is a percent of stormwater that enters the Almendares River. Then we determined the area in hectares using the GIS methods discussed by Eric. After, we determined the event mean concentration of nitrogen and phosphorus in the runoff, which is the average concentration of nitrogen and phosphorus in the stormwater for the average rainfall event. Then we multiplied these values and we were able to obtain the nutrient load of nitrogen and phosphorus per year from the city of Cotorro and the agricultural lands in the Upper Almendares watershed. Together, these two sources of pollution contribute 1.4 million kilograms of nitrogen and phosphorus each year to the Ejército Rebelde Reservoir. So where does that leave the current water quality state of the reservoir? Well, surface water bodies are in one of three trophic states, and that depends on their nutrient loading and the average depth of the water of body, which in the case of the Ejército Rebelde Reservoir is 15 meters. A eutrophic water body is one that is highly contaminated with nutrients and is usually has murky water, where an oligotrophic water body is one that does not have high contamination of nutrients and usually has crystal clear water. A mesotrophic body of water is in the intermediate state, and this is the desired state for the Ejército Rebelde Reservoir. So currently, the Ejército Rebelde Reservoir is strongly eutrophic, and when we compare this to more familiar water bodies like Lake Okeechobee and Lake Erie, before they were federally mandated to be cleaned up by the federal government, you can see that the Ejército Rebelde Reservoir is much more eutrophic. And this, unlike the Lake Okeechobee and Lake Erie, the Ejército Rebelde Reservoir has not been cleaned up, and this is a major public health concern. So to address this, we recommend to transition the Ejército Rebelde Reservoir to a mesotrophic state, which is the desired state. And to do this, we determined that a 90% reduction in nutrient loading of nitrogen and phosphorus would be required. So to do this, we determined that using riparian buffers would be a low-cost, low-maintenance, sustainable solution. Now, riparian buffers are vegetated areas along the banks of rivers which act as a natural biofilter, preventing nutrients, sediments, and even fecal matter from livestock from entering the Almendares River and being transported to the Ejército Rebelde Reservoir. So to achieve a 90% reduction in the nutrient loading, we determined using the U.S. EPA design guides, the U.S. Army Corps design guides, and the Department of Agriculture design guides that a 40-meter wide buffer, or 130 feet wide, with a slope under 5%, and permeable topsoil made up of 3 zones that the first will provide stream bank stabilization, the second will absorb the nutrients, and the third will provide runoff control, will allow for the 90% reduction to be achieved. And now Sergio will speak about the results.
So as we can see in our results, we were able to lower the volume of contaminant entering the reservoir by 90% and achieving the desirable state of a mesotrophic water body that is acceptable for a tropical water body, such as the Ejército Rebelde Reservoir. And when we began this project, we had 4 goals in mind. We wanted to quantify the non-point loads, and we were able to do this through development of GIS techniques. We have technology that was readily available for us. However, we used it in a way that no one has ever done before. Furthermore, we wanted to determine the status of the reservoir, and through literature review and our contaminant loads, we were able to determine the current status and health of the water body. We designed a riparian buffer as a suggestion from Dr. Juan Bueno, and in analyzing its performance, we can see that it works. We get over 90% reduction in the load, and we achieve our initial goal. Thank you very much, and with this, we will begin the questions.
Make sure you stay